Well, any questions? Okay, so in the last lecture, we saw toward the end a very generic property of conformal field theory, which is the OPE between two stress tensors and generically takes the form and we focused on the first term, which does not follow from the standard behavior of a primary operator. So this is telling us that this is not a primary operator. And this coefficient here contains this constant C that is called the central charge of the conformal field theory. And we saw that for the free boson, which was the example that we were looking at in detail, this coefficient is 1/2. So C in this normalization is 1. And so that's the statement that you see often, that the free boson has central charge 1. Right. We'll see other conformal field theories. And so when you are presented a two-dimensional conformal field theory, one of the first things you want to do is to do this calculation to see what the conformal, what the central charge is, right? And remember the motivation for doing so in the string theory context is that we would like to have a conformal field theory description of our string dynamics in such a way that this coefficient is 0 totally, right? So that conformal invariance is preserved at the quantum level, and which means that the at the end that the Weil invariance of the original ungauged fixed action is preserved, right? So that's the goal. Let me briefly go through some more CFT technology, which maybe starts being familiar by now, right? So because it's very similar to what we did for the X for the boson. So you can take the stress tensor and you expand the stress tensor in modes. Right? So this is similar to the mode expansion of the bosons that we had. Traditionally, the mode of the stress tensor are called L. And you see that this shift is very similar to what we had for the boson. For delta X, this is something that I was mentioning yesterday, right? The mode expansion for delta X was this, right? So this term, this extra shift, as I mentioned yesterday, comes from the Jacobian, from the W coordinate, the cylinder, the coordinate, to this Z coordinate where the worksheet is the complex plane, right? So if you think about that step, that term which comes from the Jacobian is as a power that is the conformal weight, right? So the Jacobian is dW over dz, actually dz over dw, power h. So in this case is 1 because the conformal weight of the x is 1, right? Since t is dx dx, so as conformal weight 2, right? As standard to put a -2 here. Right? It plays exactly the same role of -1. So for a generic operator O, a primary operator of dimension h, I will write a mode expansion that is like this. Right? So if you wish, another way of saying is that these modes are the natural modes in the tau sigma parameterization. Right? So it's the standard Klein-Gordon expansion for the scalar or for an operator in the W coordinate. Very good. So in the this object here play an important role. Of course, okay, let me say one more thing, because there were a few questions toward the end of yesterday. Here I'm focusing on the holomorphic part of the theory. Right? Everything I'm saying, it also holds for the anti-holomorphic part. So we will have, beside t, we will have a t tilde, which is function of z bar. This object will be expanded in the very similar way in terms of L tilde, right? So everything is carries over for the anti-holomorphic part. And then, once you have the two sectors explicitly written, you have to make your choice, whether you are describing a closed string or an open string. If you're describing a closed string, this sector is independent, right? These objects are independent of that object. If you're describing an open string, then the boundary condition, exactly as they worked for the delta x, they will work for the other operator, and there will be an identification between the anti-holomorphic and the holomorphic part. Right? And as I mentioned yesterday, the identification for the L tilde is that they are always equal to the L for the open string case, both for the Neumann and for the Dirichlet case. And you can check that very easily because this L tilde, delta x, so the sign appears twice. No. Very good, yes. So a primary operator is determined by h and h bar, right? So the example I'm giving you are kind of special because one of the two is 0, right? So this delta x, as if you let me write h bar, so this is 1, 0, right? So this is 2, 0. But you can just multiply, right? Have things like, and we will have dx d bar x. This is dimension 1, 1. Right? So that object depends both on z and z bar. Right? So it's really completely independent, and then you can just combine them. More questions? Good. Okay, so what I want to do, what I want to stress, and then I leave it to you as an exercise to fill the detail. I filled the detail yesterday, so if you want, I'll print the solution for you, and then you can check. Right? So it's instructive to make the connection between the modes of the stress tensor and the generator of the diffeomorphism in 2 dimensions. Right? So this is something I mentioned as a fact, saying you can think about this object as the generator of the diffeomorphism, and in particular, what I'm saying is that Ln generates the transformation z goes to z prime equals z plus epsilon zn plus 1. Right? So this is an infinitesimal diffeomorphism. Epsilon is a very small quantity. And what I'm claiming is that this infinitesimal transformation is generated by Ln. Right? So for instance, L minus 1 generates just the shifts, the translations in 2D. Now, how do you check that? Well, in the standard way, the transformation, what you can do is to check this statement on a primary operator, right? So if you remember, yesterday I was saying a primary operator is an operator that transforms. Let me do it on the left part. Is an operator that transforms right? Like that. So what we want to do is to check that the commutation relation between Ln and O, this is what is induced by, so if Ln is the generator of this transformation, then the commutation relation between Ln and O should be just the variation of the operator due to this change. And this variation is nothing else than O prime in Z minus O in Z. Right? So this is what we want to check. If this is true, then Ln is indeed the generator of a transformation that is the infinitesimal version of that. So the exercise is first calculate this d delta O by taking this definition and defining Z prime in this way. So you just have to do Taylor expansion, right? Take epsilon small. And you will have two contributions. One contribution is coming from this, where you have to do the binomial expansion, right? And the other contribution comes because this is O prime of Z is also coming from inside here. So you have these two contributions, and you can calculate this in the first way. The second way is to calculate this commutation relation by using the OP, right? So you can write this object as the integral of T Z1 over O, and this is integrated over Z1. O is in Z, so this integral is around Z. And then I want to select the nth mode, so I have to multiply by Z1 n plus 1. Right. So this is a contour integral, right? This contour integral select the nth mode, right? Because I'm using that expansion. So Z minus n minus 2 plus n plus 1 gives Z minus 1. And then I'm using the technology I introduced yesterday, right? So I would have to do a contour that includes Z, a large contour, and then in order to calculate the commutator, I have to subtract the small contour inside. Then I can take the difference, deform the contour, and that's why the contour I'm interested in is around Z. Right? Then at this point, you can use the OPE expansion that is written up there. No, it's not written up there, but I brought yesterday, right? Between T and O, definition of primary operator. And then you can use Cauchy theorem. This is a page of calculation, half page and half page, and you can see that the two things are the same. Very good. Any question about the exercise? So this explicitly shows that the L's are the generator of the diffeomorphism. And so you can, again, use the same technology to recast the first OPE up there in terms of commutation relation, right? So you can think of L as generator of a symmetry, the diffeomorphism, and you want to see what algebra this symmetry form, right? So the algebra is just the commutation between two different symmetries. So what you can do is to calculate Ln and Lm, right? And again, let me write very quickly this commutation relation as in terms of the OPE, right? So what you do, you have now two integrals. You want to promote this to a t and this to a t. So you have an integral with respect to z1, an integral to respect to z2. And the first one is t z1 z n plus 1. The second one is t z2 z n plus 1, right? And now what is the contour? Well, if you want the commutator, yeah, the usual thing, the Z1 that is related to the n has to do first the big circle, that includes the Z2, and then the small circle. You can deform the contour, and so at the end, the contour integration of Z1 is, so let me write it this way, to 1. The contour integration of Z1 is around Z2. Right. So you have Z1, Z2. I have to do first this and then this, right? And so I can plot the contour like that. This guy is this guy. It's going around. And then after I did this calculation, the Z2 integral is just around 0. Right? There is nothing else to do. Right? And again, you can start doing the first integral by using the OP. And the singularities of Z1 that goes to Z2 come entirely from that relation up there. Right? You get rid of Z1, you get something that contains just Z2, and the second integral of Z2 around 0, you can just doing it by using that mode expansion, right? T equals something, and then you have to find a simple pole. The result of this calculation is the famous Virasoro algebra. This is the first bit. So this bit arises from the last two terms of those of that OP. You see, the last two terms are both proportional to t. So if you expand t, it will be linear in the L. Right? So this term, which is linear in the L, comes from the quadratic and the simple pole in the OP. Now, what about the quartic pole contribution? You see, the quartic pole contribution is proportional to a constant, and there is no t. Right? That's very easy to calculate in this language. You can see by naked eye. Right? So if you contract these two and you look at the quartic pole, then the Cauchy theorem tells you that you have to expand. Sorry, this is 1 and 2. Sorry for that. Right? This is Z1 and this is Z2. The Cauchy theorem tells you that you have to expand the coefficient of the quartic pole such that you get a simple pole. So you have to take, so this guy and this guy gives C over 2. C over 2 times the quartic pole. So you have to take this term, Z1 to n plus 1, and you have to expand around Z2 in order to transform the quartic pole into a simple pole. So you have to go to the third order in the Taylor expansion, right? So the third order in Taylor expansion is the third derivative, and the third derivative is n plus 1 times n minus 1. Right? You have to do the third derivative of this. So this gives you z1 plus 1, sorry, n1 plus n plus 1, n minus 1, right? And then you have to divide by 3 factorial. Is that clear? This guy becomes C over 2, 1 over Z1 minus Z2 to the fourth, right? And now I have to expand this Z1 in Taylor around Z2, right? So I have a constant term, a term that goes like Z1 minus Z2, Z1 minus Z2 square. I have to look at the terms that goes like Z1 minus Z2 to the cube, right? Which is the third derivative of this. The third derivative of this is that. Right? And at the end, I will get Z2 to the n plus m. The third derivative here gives a minus 2 at the end, n minus 1, n plus 1, n minus 1, n minus 2, and then plus 1 from here. And then there is C over 2. Okay, this goes away with the Cauchy integral of Z1 around Z2. And now I'm left with the integral over z2. And this is 0. This is 1, sorry, only if this coefficient is, if this term is minus 1. So basically, if n and m cancel. Right? If n and m cancel, this is minus 2 plus 1, and then you have a simple pole, and then you get a non-zero result. So the anomaly term up there gives a contribution which is c over 12, 3 factorial times 2, and then delta n plus m, 0. So this is, you see, you start seeing this is an anomaly is deforming the algebra of the symmetries. So this is the Virasoro algebra, and sometimes these are called Virasoro generator. Any questions? Yeah, please. These ones. This one. So in this equation. Oh, sorry. Oh, thank you. Thanks. Of course. Yes. Thank you very much. I was looking at the Z. I was all focused on the Z. Yeah. Yeah. Very good. Yeah, that's important. Keep an eye on me. Yeah? So this is telling you something that I wanted to mention now. Right. So this anomaly term, right, vanishes in the case minus 1, 0, 1. Right. This is what it is. So there is a subgroup of the algebra generated by these three terms, L minus 1, L0, and L1, that is closed. You can see that they stay L1 commutator, L0 is L1, right? But it's a group that is closed, and it has no anomaly. So this will come back in the next lecture. The other comment I want to make is that you may ask, and this is something I will not use, but it may be useful for those of you who want to do CFT. You may ask, what is the meaning from the point of view of transformation of the OPE that is up there, right? You can see that OPE as an infinitesimal transformation on the stress tensor, right? We said, okay, the stress tensor acting on operator is implementing an infinitesimal transformation. And then you can say, what is the infinitesimal transformation imposed on another stress tensor, right? Is encoded up there. And then you can ask whether you can integrate that infinitesimal transformation to see the relation that encodes a finite transformation. For a primary operator, this is the answer. This is the finite transformation. Now, for the stress tensor, what is the finite transformation? That's not an entirely easy, straightforward calculation, but you can do that. And I think Di Francesco does it. And the result is this, T prime Okay, so there is a term which looks exactly like the transformation of a primary operator of dimension 2. Right? This is the term you would expect. It's exactly like this with h equal 2. But then there is a shift. There is a shift. This shift has exactly this coefficient, so it knows about the anomaly. And then there is a function here that I called S. That function is just a function that is built out of the transformation, out of the Jacobian of the transformation, dz over dz prime. It's the same Jacobian as here. And this is the result that you obtain by integrating this infinitesimal transformation. And this combination here is called the Schwarzian of the transformation. And you can check that for the SL2 transformation, the Möbius transformation that I briefly mentioned in the previous lecture, z prime equal az plus b divided cz plus d, this Schwarzian is 0. That's, again, this is an easy part, an algebraic thing you can do in 2 steps. You calculate the Jacobian, and you will see that this combination, this Jacobian to the power minus 1/2, is just linear in z prime. So when you take the second derivative of a linear function, you get 0. So this is the finite version of saying that this anomaly term disappears for n equal minus 1, 0, and 1. Right? So this is an example of something I mentioned briefly, that is the quasi-primary operator. It's an operator that transforms in the standard way for a subgroup of the conformal transformation into D, just the SL2 transformation, but it does not transform as a primary operator for the more general transformation. Very good. Any questions? Yeah, please. Yeah, that. So, do
you think that they will also give a finite result after that calculation?
So, are you asking about the terms that are in the dots, or the second and the third? The second and third term give this. Yeah. So please do that check. I'm not doing on the blackboard, but it's very similar to what I did here, right? So the quadratic pole, you just have to expand to the first order. The simple, you don't have to do any expansion, just put z1 equals z2, and then you combine, and it's interesting to see that you get this n minus m. It requires 10 minutes of being undisturbed. More questions? Of course, let me stress that the terms in the dots, they are irrelevant, right? The Cauchy if there is no singularity here, the Cauchy theorem kills them. So the important important point is that everything you need to calculate the commutator is in the singular terms. Okay, very good. So this ends the CFT summary that I wanted to give you. And so I can go back to the string application, right? And I will, in this part, so applying going to the covariant quantization of the strings, where we will see a new CFT arising. I will not go through all the algebra. I've done it just to be sure. So if you try and you have questions, please feel free to come to me. So the idea of the covariant quantization is very similar to what you do in gauge theories. So what you want to do is to define your quantum theory as an integral over a path integral over the Euclidean action, right? And let me write it in terms right. So what we are doing now, we are going back to the ungauged fixed description, right, with the worksheet metric that is a dynamical field, and we integrate over all possible values of the metric. We integrate over all possible values of the field X describing the embedding of the string. And the typical type of integrals we want to do are integrals of this type. Now, the problem that you have in defining, in giving a concrete meaning to things like that, is related to the local invariances that we mentioned on Monday. And the point is that you have different metrics, H, and different fields, X, that they are different as functions, but they give exactly the same action. Right? The action is invariant under binary scaling, is invariant under diffeomorphism. So if you sum over all possible metrics and sum over all possible fields, you will have many contributions for which this weight is exactly the same. Right? Because the action for two values of the metrics and two values of the fields is the same. And actually, the number, the locus of equivalent metrics and equivalent axes will give you the same contribution an infinite amount of time. So the naive definition, right, of this thing would be very likely some infinite result. So in picture, again in a qualitative way, if you think about the space over all possible x and all possible h's, right? Of course, this is an infinite dimensional space, so this is just a cartoon. You will have a subspace here for which you have inequivalent choices of x and h. So if you move along this subspace, this action will change. And then you will have orthogonal directions that are just generated by gauge transformations, right? So orthogonal direction where the change of h and x is just due to a diffeomorphism or a binary scaling. And so if you move in that direction, you change h in a way that is just induced by the Weil transformation. This object does not change, right? So intuitively, what you want to do is to restrict this integral on the pink region and just take away the contribution of the gauge orbits, of the direction that are defined by the gauge transformation. Now, if you want to be precise, which I will not be, you may ask, okay, give me a precise definition of this measure. And this is an important point, right? So you can think of just saying, okay, if I can do something very similar to standard quantum field theory, take a solution of the classical equation as a reference solution. Right? You can take H to be the Euclidean metric, the flat metric, X to be any classical solution of the string, and then you expand around the classical solution, and you integrate over all possible fluctuations around that classical solution, and then you want to define a norm of that fluctuations, right? And that gives you a definition of this object, right, of this measure. Now, the point is that once you want to define a norm of this fluctuation, it's natural that you use your reference metric H, right? So the norm is something, okay, you integrate over all possible fluctuation, you integrate over the fluctuation over the whole space, and the integration will have the standard root h times d tau d sigma, right? D sigma plus, d sigma minus. So you will immediately see that if you define a norm for this one, and the norm for this one is just slightly more complicated because you have to contract indices, but it's done in the same way, that definition of the norm does not respect the Weyl invariance. So that definition of the norm, because you have this root h, will not be invariant under rescaling of h. So this is another way to say why this Weyl invariance may be troublesome at the quantum level. Indeed, you have an action that gives you the probability weight that is invariant under Weyl transformation. But it may be that the measure you need to define the path integral is not. So you are breaking your invariance at this point. And so the question is, can I at the end recover something that is Weyl invariant or not? That's another way to see this issue. Okay, so in practice, what we will do is to follow very closely the standard Fadeev-Popov trick. Did you see this with Bilal? Yeah. QFT. BRST, you have seen. Yes? No. Okay, I'll go through, and if something is strange, you just stop me. Eh? So basically, the idea is, okay, let's try to localize the integral over this pink region, and basically you want to do a change of variables where this integral, even if I will not define too carefully this measure, but basically we want to do a change of variable where this integral is defined as an integral over the pink region times an integration over the gauge orbits. And then we want to take away the integration of the gauge orbits. Just say, okay, we don't do that, because that's a redundancy. We are summing many times the contribution of physically equivalent configuration. So the whole thing is that we want to change variables here, right? And we want to introduce as integration variables the generator of the gauge transformation. So let me rewrite the generator of the gauge transformation that I brought in the first lecture. So this is the effect of an infinitesimal gauge transformation generated by the vector v on the metric. And then there is the infinitesimal Weyl transformation. So these are the three parameters, v0, v1, right, the vector in 2 dimensions, and omega is the effect of the Weyl transformation, and I brought the infinitesimal version, right? And at this point, it is convenient to rewrite this by separating in these bits the trace part from the traceless part. Very good. So if you multiply, now this is a tensor in HAB. If you take the trace, you multiply by HAB when the index is up, this parenthesis vanishes, right? This gives twice, and this, the trace of H is 2. So this parenthesis vanishes. And this is the bit, sorry, this is the bit that is proportional, let me call this C, that is proportional to HAB. So this term cancels this term, and this term is that term. Very good. So what we want to do is to change this integration and introduce this parameter, integration over dv and an integration over d omega. And we do that in the standard way, as Father Popov did. So by inserting in this integral 1, right? We can for sure multiply everything by 1. But we write 1 in this funny way as an integral over all dv, an integral over all d omega, okay, so how does it work? If you take this bit and you combine with this determinant, so this is exactly the Jacobian that change the integration v and omega into an integration over h. Right, so this is exactly like saying dx prime is dx prime over dx times dx. Right. So you can cancel this one with this one. And this delta h is the variation of our reference metric h to a new metric that is obtained by doing a gauge transformation generated by dv and d omega. I think here. So dv and d omega are the thing you are integrating over. So you choose your dv, you choose your d omega, you do the calculation, then you choose another dv, you choose another d omega, you do the calculation, and you sum overall contribution. That's the definition of this integral. Right? So you have a reference metric, and then what you say, okay, I have a new metric. So this, I'm moving along this white thing, right? h is here, and hv is just shifted a bit. Right? hv is h plus this delta h. Right. So I'm moving in this gauge orbit, and then I say, okay, if I integrate over the whole gauge orbit, if I move around, and then multiply by this Jacobian, right? This is basically changing this measure into a measure with h, and then the integral over dh times the delta function is just 1. It sounds tricky, but okay. That's a complicated way of writing 1. And this is useful because if now here you take this one and you write in this form, you see what you can do. You can use this delta function to do the integration over h in an easy way. So you get rid of the integration over h, and you are left with an integration over the gauge parameters. And so in this way, you can change the integration variables from the metric to the gauge parameter, and the hope is that at the end you can get rid of the gauge parameters. Now, you do that, but you pay a price. And the price you pay is that when you insert this here, you are including this determinant. And that's an awkward thing, right? Of course, if you want to give an explicit expression of your path integral, you need to be more explicit about what this determinant is. So you do that in the following way. Right. Think about that determinant as a functional operator that acts on the gauge parameters. It acts on delta v and it acts on delta omega. And you see that is composed of two actions. One action which is that round parenthesis, And that's a differential operator that acts on vectors and gives you back an object with two indices. So the round parenthesis, it acts on dVA and gives you back an object with indices AB. Right? You see it from the parenthesis. And this object is traceless. And the second action is the second bit. It acts on the metric, on object with two indices, and gives back an object with two indices. So these are the two actions for this operator at the numerator in the determinant. And so you can write it explicitly, the determinant, right? So if you let me call this first operator big P, so the big P is defined by that parenthesis, the determinant looks like the variation of P with respect to dV, the variation of P, let me write it this way, the variation of P with respect to the omega, and then the variation of the second parenthesis. Here, let me give a name to this object, to the omega tilde, to the omega tilde over dV, and here to the omega tilde to the omega. So I just brought this determinant, right, splitting in the two terms, and you see that this contribution is zero, right, because the definition of the parenthesis there that gives the operator that maps object with one index into object with two indices does not depend on omega. So this determinant is like a triangular matrix. And so you can say that the determinant is the product of this determinant times the product of this determinant. We are not interested in this part. Right? So this term we don't need to calculate. This term is very easy to calculate because you see that omega tilde and omega are just proportional to each other. So the derivative of this term is just 1. Right? You see it from there. And this is the hard term. So this is so the determinant here is this. Now, the key trick is that, and this is where anti-commuting variables arise, is that we write an integral expression for this determinant. So if you have a standard matrix, a 2x2 matrix, and you have the determinant of that matrix, you can write the determinant as the integral over Grassmann parameters of the exponential of the matrix. Now we are doing the very similar thing here. So we write this as an integral over Grassmann functions. So these are objects that get assigned when you swap them. And this function here are exactly a Grassmann version of the object on which P acts. So this differential operator acts on object with one index. And so we take this gauge parameter and we promote it to a Grassmann variable. And that's going to be the C. CA. Now, the a result of the action of P is an object with two indices, and we also promote that object to a Grassmann function, and this is B. And then we have here the exponential of the operator of P. Very good. Now I have, okay, before putting the indices, let me see whether the idea is clear, right? So we take the operator P, and we write the determinant by introducing Grassmann parameters that are nothing else than the object on which P acts and the object that P gives you, right? So if you do this on a 2x2 matrix, right, you will see that you get the determinant of the matrix once you do the Grassmann integration. So we do the very same thing, and this P is defined by that parenthesis. So you see it's an operator that is linear in the derivatives. Each term contains just one derivative. It acts on vectors, and it produces traceless tensors. So if you define BAB to be a traceless tensor, you can simply write this exponential. The normalization is pure convention. You can simply write it this way. So what I brought here is nothing else than that parenthesis, where every time you see dv, you write c, and that parenthesis is multiplied by BAB. Yeah. So what I'm defining this thing, maybe this is just a bad notation. This object here, I define P acting on dv. Right? This object, P, the operator is just the derivative. Right? And this parenthesis is the action of the operator on something. Right? So this object here is just to say you have to strip dv. You just have to get the operator. It's very similar to what you do in gauge theories, where the determinant contains the gauge condition, and you have the derivative on the gauge parameter, and then the operator is just the covariant derivative itself. And then you introduce ghost, and you have the determinant of that covariant derivative. More questions? So what I'm saying is that this is just one line of algebra. If you call this guy C, right, and then you multiply everything by BAB, you can match that is the same as that. So the final, so you see that here we are getting a new sector of the theory, B and C. That's the information. Right? So the final message is that once you do the covariant quantization, you have the X degrees of freedom, but you have extra degrees of freedom, B and C, that are there to take care of the gauge invariance. Exactly as in a gauge theory, you have the electromagnetic field, the gauge field, A mu, but you also have the ghost. Okay, let me make a series of remarks. Okay, first remark is that if you think a bit, just very qualitative, you may say that an equation like that doesn't make sense. Because this operator, this derivative, does not look like a square matrix. Right? What is a square matrix? A square matrix is something that acts on a vector space Vn and gives you another vector in Vn. It's a square matrix. This object, this P operator, it acts, as I say, on object with one index and gives you traceless tensor. So the target space is different from the original space. It looks like a rectangular matrix, right? You act on Vn and you get Vm. You get an element of another space. And what is the meaning of the determinant of a rectangular matrix? Okay, so that's true. And indeed, we are not really calculating the determinant of P in this way. More precisely, we are calculating the square, so this object here calculates the square root of the determinant of P dagger P. What does it mean? How do you get a square matrix from a rectangular matrix? Well, you take this rectangular matrix and you multiply by the conjugate. At that point, you get a square matrix, right? So you go from this space to this space, and then you go back from this space to this space. Of course, if the matrix was a square to start with, the determinant of P dagger P would be the determinant of P square, and the square root would be the determinant of P. Right? So this is very similar. So this object is calculating a determinant, is actually calculating this determinant. This is first information. Second information, you say, well, it's common that the determinant is 0. When does this happen? It happens if your operator P has 0 eigenvalues. Right. The determinant can be a very complicated thing, but as soon as you have just one single 0 eigenvalue, you know that your determinant is 0, because the determinant is just the product of all possible eigenvalues. Right. And indeed, in this case, and in many cases, this is what happens. So when we are actually writing this determinant, we are writing more precisely the product of all the non-zero eigenvalues. So sometimes when people are fuzzy and precise, they put a prime. So the 0 eigenvalues, or if you want the corresponding eigenvectors, will need to be treated separately. And you will see this very explicitly in the string amplitude. Right? It's in this application, it will be very transparent. So the corresponding eigenvectors they need to be treated separately. Very good. So I can conclude this first part. Yeah. Sorry, say it again. Delta P. Oh, here, this P. Here, this determinant. Sorry, I realize my notation is a bit confusing. So this object here is just the variation of P with respect to dV. Yeah, I think this yes. I think I should take away this. Yes. Thank you. So basically, yeah, sorry, my notation is a bit messy. So what I'm just saying is that I take that parenthesis and I want to strip away delta V. Then you have a differential operator that is linear in the derivative. I want to calculate the determinant of that differential operator. Yeah. Okay, so let me conclude by writing what we are actually after. Right? So we have the original action that is up there. Then we have this new action. Then we had a delta function, which is this one. Then we have this integration. And then we have all integration over x and h. And so what you can do is you take your reference metric to be the flat metric, right? To do this integration to put everything here the flat metric, so you can write these in the gauge fixed version, exactly as we did for this term, right? And then the hope is that we can throw away this bit. So this ungauge fixed action is still useful, and we will use it for the next 10 minutes, because from here we can get the stress tensor, right? The stress tensor is coming from the equation of motion of h. Remember, we derived for the x, the variation of the action with respect to h. So now you will have a contribution of the stress tensor coming from here, which is the one that we already calculated, and then an additional term that comes from this bit. Once we calculate the stress tensor, right, then we can repeat the same steps as we did before. We fix the gauge, we do this integration, fix the gauge, and then work with a conformal field theory, right, in the gauge fixed action, in the gauge fixed language, where now you have two sectors that people call matter sector. From the 2D CFT point of view, these objects look like scalars. And this is the one that we had discussing so far. And then you have this new sector, which people call ghost sector, that comes from this Fadel-Popov description. More questions? Okay, so let's take 5 minutes, but let's please be 5 minutes. Ho schiacciato questo. Ho fatto bene? Ok. Okay, can we start? Okay. Very good. Okay, so always keep an eye on me, as someone correctly pointed out here, the final equation, I forgot this, the integration over B and C. Right here, of course, we are integrating over these fields, right? So I brought this equation because this is the standard form you see usually in books, and then I claim that okay, the first thing we want to do, which I will not do in all detail, but I will tell you how it works, is to take this new action and find the equation of motion for the h, right? And that will define the stress tensor of the new conformal field theory, including the ghost sector. Right. So if you just do the calculation by taking the derivative of h from here, you do not get the right result. So what is right meaning the same thing that books write, right? So, what is the problem, the caveat? Right? The caveat is that these object ears, C and B, have indices. And so you have to be careful what you keep constant when you take the variation of h. So CA is by definition HAB-CB. So it is not possible to keep both this guy and this guy constant when you change h at the same time. Right? Because the CA with an index down hides a factor of h. So you have to tell me what are the fields that you keep constant, where are the indices, whether they are up and down, when you take the variation of h. So that's why this ghost action in the ungauged fixed form is written like that, and not with indices down for C and B with indices up. It's written like that because it is suggesting that what you need to keep constant when you take the variation with respect to h are so keep constant CA and BAB. Right, so this is the first piece of information. But this is already implemented here. So I'm just telling this in order to explain why when I was calculating this bit, I brought it in this form. Right? It naturally comes out in a slightly different form, but we write it in this way so as to make clear that this field and this field are kept constant when you take the variation of h. Still, there is a second caveat. As someone pointed out correctly, in order to write this form from the original definition of the operator P, we need to use explicitly the tracelessness condition. Right? So if you start from, someone already did the exercises, you start from the parentheses I wrote, and then you write this action B, P, C, and there is one extra term, and your extra term is 0 because you use the fact that this B is traceless. But the traceless condition is a condition defined with the metric. Right? The traceless condition is BAB, HAB equals 0. So when you change H, you are spoiling the traceless condition, right? So you had a B that was traceless with respect to your reference metric. Now you change the metric in order to calculate the derivative, and the B in the new metric is not traceless anymore. So what you need to do is to write an action that is equivalent to this one and equivalent to the original one, where you do not need to use the tracelessness condition. Right? And then, at that point, you have an action that does not have any reference to the metric, and you can take the variation of the metric. So this is easily done. So if you want, and this is useful just for this calculation, then you can forget about it. If you want to derive what the stress tensor is, it's better to start from an S-ghost, which takes this form. Right, so I added here a term that is obviously 0 because it's HAB-BAB. So you can kill this term, and this is C, right? You can kill this term, and then you go back to the original equation here. But if you don't use that BAB is traceless, so if you multiply this square parenthesis by a trace, something that is proportional to HAB, this is automatically 0. So this is a form of the action which is equivalent to this one and allows you to be completely arbitrary. It automatically selects the traceless part. Here. Oh, yes, sorry. Yes, thank you. Yeah, so this, I even said in words, but of course it didn't match the writing. So if you impose this B to be traceless, this term goes away, and this is exactly that. What I'm saying is that this is equivalent to what we want, even if B is not traceless, because the trace part is automatically projected out, right? So if you choose BAB to be any constant, any function, times HAB, right? And then you multiply this here, you will see that they go away. Very good. So the answer is that if you take that as a starting point, and you do the variation of the ghost part with respect to HAB, you will get this answer, -2. And I write this answer, then you get an answer in the ungauge fixed form, but what we will be really using is the gauge fixed, so I just write the answer after I fix H to be the flat metric, right? After I did the derivative, I can evaluate it on the reference metric, and so evaluate it on the flat metric. And what I get is BZZ DCZ plus DBZZ CZ, right? So this is the variation, this is the variation AB after you choose A and B both Z. And then, of course, you have the same combination with Z bar, right? And then you have the same combination with Z bar and D bar, right? So this is TZZ, ghost, and this is TZ bar, Z bar, ghost. And of course, the third component, TZZ bar, is 0, exactly as it happened for the matter sector. So at least conceptually it's clear, right? So we write the action, we write it in a covariant way, we take the variation with respect to H, that's the equation of motion of H. This is something that we need to add to the contribution of the matter sector. We evaluate that result for the flat metric, our reference metric, and the result of this algebraic operation is this object here. Right. Any questions? So let me quote, also give the result for a more general case. It will be useful later. So this is not something that is motivated now from the point of view of the quantization of the string, but you can think about that case. So you can easily generalize this action to a case where this object B, instead of having just 2 indices, has a bigger number of indices, B, A1, A lambda. Right? So the case we have been doing so far is lambda equal 2. And then, if you want to write an action of this type, then C has also a lot of indices, but is one index less than B. So the final one will be lambda minus 1. Right? And then you can write the same action where these lambda minus 1 indices of C are contracted with lambda minus 1 indices of B. Right? Exactly here, like this one is contracted. Right? And then you say, okay, let me do the same for all the others. They are all contracted with the B. And then the B has an extra index that combines with the derivative and is contracted with the metric. Right? So you can do that more general case. And then you can repeat the same derivation for the stress tensor. You have to write, again, the metric in a way where this object is traceless in any pair of the indices. So it's a bit of more combinatoric work. The thing that we have done for these two, you have to do it for the any pair. Once you have that starting point, you just do the algebraic derivative. And you get to a definition of the stress tensor that now depends on lambda. And let me quote what the result is here. It's very easy to remember the full case because lambda generalizes to 2, so that factor of 2 becomes lambda. And this factor of 1 was related to the other number that we had, the number of indices here, that is lambda minus 1. So the logic is that after introducing the Gauss sector, and after calculating what the stress tensor, the equation of motion of H, are, right, we can do the integration over the metric and try and fix the conformal gauge. And if you do this on the action, this action will become so this is the gauged fixed action. Right? All this factor of H disappears, and this is written in the complex coordinate D2Z. So the final, the outcome of this Faddeev-Popov description is that once you write the gauge fixing term in terms of the Gauss, the result is again in the flat gauge, a conformal field theory, but now containing a matter sector and a Gauss sector. And the Gauss sector is a theory of fermions, anti-commuting variables, that came from the Faddeev-Popov prescription. And is again a free theory. You see, this looks like Dirac equation, right? Just one derivative with no mass, no potential term, right? So this is just a free theory. Now, let's look at the conformal weight, right? So this guy has conformal weight 1. h equal 1, and this guy has conformal weight h bar equal 1. So this is an object that has conformal weight 1, 1, and the measure that is a measure on dz bar, right, has conformal weight -1, -1. So they match to have something that is conformal weight 0, right? So the action is a scalar, is invariant under dilatation. Now let's check this object, right? What is the conformal weight of B? Right, B is an index that is a field that has two indices down. So B looks like 2dz. Right? It's like this guy with two derivatives. So this B has conformal weight h equal 2. And C seems the opposite, as an index up. So it behaves like a coordinate, like zeta, right, is an index up. So this guy has assignment of conformal weight -1. So you see that H has conformal weight 2 plus -1 is again 1. And D bar has H bar equal 1. So again, this term, from the conformal field theory point of view, has dimension 1, 1, exactly as this one, and so it can be integrated over d to z. And this one just works in the opposite fashion, right? This is h bar equal 2, this is h bar equal -1, and this is h equal 1. You can check this very explicitly by calculating the OPE of this stress tensor with B and C. Right? So if I claim that B is a primary operator of dimension 2, it has to satisfy the relation T ghost an operator. This has the OPE, Z1, Z2 is H, or Z2 divided Z1 minus Z2 square plus DO Z1 minus Z2 dot dot dot. Right? So what you can do is to take this expression for T, evaluate it in Z1, and then have take O to be B, look at the quadratic pole, and see whether this coefficient is 2. In order to do that, in a very similar fashion as we did for the matter sector, I have to give you the OPE of the elementary fields. Right? If once I give you the OPE of the elementary fields, in a free theory, any complicated operator is a combination of the free fields. And so you can do the calculation just by using big theorem. Right. So the OPE of the elementary fields is very simple, and is this one. Now you can check this OP makes sense by looking at the conformal weight. Right? This has conformal weight 2, as I mentioned here. C has conformal weight -1. So globally, this object has conformal weight 1. And so the right-hand side better to have the same conformal weight. And this is 1 over Z, so it's conformal weight 1. I'm a bit on this because the flavor is very similar. I'm just saying the result of this construction is to add an extra sector to the CFT that is again free. And so you can do the calculation in a very similar pattern as we did for the matter field. Very good. So the key calculation that we want to do is to calculate the OP that is up there. Right. So, yeah. Yeah, this H is the conformal weight of this, O as conformal weight H. So I just brought the general version because if you put O to be B, you will have H equal 2. If you put O to be C, you will have H equal -1. So when you do this calculation in these two examples, this quadratic pole should have a different coefficient between the two. And this should follow from this two contribution. They should combine in a slightly different way. More questions? Yeah. Yeah. We will go through this, yes. So you will see, this is a very interesting question, right? So we will now do the quantization in this language. Right? And then I will tell you how the old quantization fits in this new language. Yeah.
The formula for operator product expansion doesn't hold if you set O equals to T, right? But if you neglect to include the Cauchy pole.
Yes, exactly the point. So what I'm saying is that T is not a primary operator. Yeah, so the point that you said is comparing this formula with that formula. T naively would be an operator 2, but since T does not satisfy this relation, then you cannot say that T is a primary operator. Yeah, you can do the check, right? You see almost by eye, right? Because you see the when you contract, you put here B, right? The worst possible singularity comes from this guy. DC contracted with B. C contracted with B is a simple pole. You take the derivative, is a double pole. But all these things is very important, right? You want to check once, right? And then you see, okay, that it works. Everything is super explicit. Very good. So here the calculation is not complicated, just requires a bit of patience, because you take this T here, the same version here. You have 4 terms. You have the first with the first with the second with the first, second with the second. And you have to be careful with signs. There are 2 sources of signs. If you happen to swap a C and a B, right, then you have a sign. And the second source of the sign is when you take these derivatives, right? So when you take the derivative, if you are taking the OPE of B and DC, you are taking a derivative with respect to Z2. That derivative does not bring any sign because you have one sign from the fact that this is a denominator and another sign because you have that. But if you act with the derivative on the first, you'll get a sign from the derivative. So just be careful with this set of signs. And the result of the quartic pole, and let me write it in 4 terms so you will be able to check. Right? So this bit comes from this square. This bit comes from this square. And the final bit comes from the 2 cross products. I wrote this for generic lambda. And then you can evaluate for lambda equal 2, which is this case. Right. So let me do the algebra here, because then this will come back. Right, so we have minus lambda square minus lambda square minus 4 lambda square from here, and from here. And then I have plus 2 lambda from here, plus 4 lambda, and then I have minus 1. So this is minus 6 lambda square plus 6 lambda minus 1, which I can write as minus 3 2 lambda minus 1 square plus everything half. Right? So 4, 5, 6, 6. Then this is 4, 3, 12 divided by 2 is 6. 4, 3, 12, 6. And then minus 3 plus 1 is minus 2 divided by 2 is minus 1. So this is the value of the quartic pole. So this is the bit that multiplies 1 over z1 minus z2 to the fourth. And then there are the other terms. The other terms, please calculate them once, because it's not entirely trivial that they will satisfy this extra 2 term that you get for the quadratic bit twice the original stress tensor, and for the simple pole exactly the derivative of the whole stress tensor. Right. Now, this coefficient here is important because you see that coefficient there is a new contribution to the central charge, to this anomaly. Right. And this, since this is defined as C over 2, right, then the C is this. It's C. This is the central charge. So this C has nothing to do with this C, sorry. It's just that people use the same. That's the central charge. Now, one thing which is nice is that this central charge for lambda equal 1, 2, 3, 4 is negative. Right? Because you see, this object here is positive, multiplied by minus 3, becomes negative, and dominates over this. So we are going in the direction that we like, right? So this is a new contribution to the central charge. This new contribution is additive, right? Because the total stress tensor is the stress tensor of the matter plus the stress tensor of the ghost. Right? So when you, right, this, so the total T total is T of the X that we calculated plus T of the ghost. Right? So this is because these two theories you see are completely decoupled, are two free theories. Right? Free theory for the matter, free theory for the ghost, completely decoupled. Right? So we calculated a factor of C here, and the C that we obtained here was 1 per each boson. Right? So we got the quartic pole was 1/2, which means C equal 1. So the contribution from here is 1 times D. Right? Because in string theory we have xm, so we have a space-time index, and that space-time index goes from 0 to D minus 1. So this is the number of space-time dimensions. This is the contribution to the anomaly that comes from the matter sector. Now, the contribution here is negative. And for lambda equal 2, let's see, is 2 times 2 is 4. 4 minus 1 is 3. 3 squared is 9. 9 minus 3 is minus 27. Minus 27 plus 1 is minus 26. Right? So what I'm saying is that this quartic pole gives 26 over 2, so the central charge is 26, minus 26. And so you see that you can define an anomaly-free CFT description if D is 26. So if you force this to be 0, because you want to preserve the symmetry at the quantum level. In this way, you preserve the original Weyl invariance, the local symmetry at the quantum level. Then if you fix this C, the total C, to be 0, then this gives you a constraint on the dimensionality of space-time, and in particular tells you that this has to be equal to 26. So this result was first derived in a completely different way, and it's a very surprising result because it's something that are not used in standard quantum field theory, where you can have different space-time dimensions, but it comes from a constraint related to the worldsheet local symmetries. So we will revise this calculation when we do superstring. Right? Now you can guess in the superstring there will be new local symmetry, so we will add more terms here. They will be again described by free CFTs, and they will be again decoupled. So the calculation for the critical dimension, so the dimension of space-time which ensures that there is no anomaly in the superstring, will have extra contribution here. And at the end, we will see that in that case, the result is d equal 10. But conceptually, there is nothing new. And the superstring conceptually will be very, very straightforward generalization. With this, just be technically more challenging to do the explicit calculation. Any question on this point? So, sorry, why? Lambda equal 2. Two. Right, there is another 2 here. Yeah. No, it's crucial. So here I wrote the generalization just because it will be useful in the superstring. Basically, it will be very similar with a different value of lambda. But for us, for this lecture, right, you can always forget lambda, put lambda equal 2 everywhere. That was fixed by the properties of the gauge parameters. So that lambda equal 2 is because the symmetry is diffeomorphism, is a vector, so is equal, the C as conformal weight minus 1, and then the adjoint thing, the B, has to be 2. So that's fixed. Yeah, very good. Yeah, sorry for that. More questions? Okay, so what I want to do in the end is just have some further comments on the BC system and give you the link to the operator language. And this will again point toward the issue of the SL2 transformation, the zero modes. This will come back. So what you can do is to write the mode expansion for B, right? Again, everything I do is for the holomorphic part. The anti-holomorphic part is the same, right? So you can write the mode expansion for B. And according to the general rule, right, since this has conformal weight 2, I will put the minus 2 here. So it's very similar to what we did for the L's. And then you can do the mode expansion for C. And instead of here is minus h, minus the conformal dimension is minus 1, so minus 1, I put plus 1. Now, exactly as we seen for the matter sector, this OPE is equivalent in the operator language to the canonical commutation relation on these modes. Right? Of course, in this case, since these are fermions, instead of commutation relation, this is, sorry, Bn. Instead of commutation relation, we will have anti-commutation relation. So we will have things like Bn Cm. Right. Now, this commutation relation tells you that there is a bit of a subtlety in defining what the vacuum of the Fock space is. Now let me show you where the issue is. So you have C1, right, and B minus 1. And B1, sorry. Okay. Right, so if you naively think, okay, I want to define this guy to be 0, right, because C1 and B1, right, this implies that also the conjugate should be 0. But then, if you take the scalar product of these two objects, right, you would then conclude that that this scalar product is 0 because these ingredients are 0. But then this is in contrast with this commutation relation, right? Because this is equal to this. Which is this. Which we would like to have to be 1. So we have to be careful in what we define to be, how we define the vacuum. And the idea is that the vacuum is defined as follows. So you see that there is something special going on for the sector -1, 0, 1. Right? The sectors that goes in general from 1 minus lambda to lambda minus 1. For lambda equal 2, there are these 3 oscillators. You see, it's a bit asymmetric in that sector. For n bigger than lambda, everything is standard. Then you for n smaller than 1 minus lambda, so -2, -3, everything is standard. But in the middle, between 1 minus lambda and lambda minus 1, right, we choose this object. Right? So, okay, sorry, I said this the opposite way. It's a bit after the 2 hours. I said this the opposite way. Okay. Let me take 5 minutes to correct what I said. Okay, so this is the standard definition. Standard definition. Right. So, for lambda equal 2, we have indeed that this vanishes on the vacuum for -1, 0, 1, 2, 3, 4, etc. So this is indeed 0. Right. And this is also 0, right? According to this definition. So this follows from here. This follows from here. So this is 0. This is 0, right? Because b minus 1 on this one is 0. B minus 1 on the right is also 0. So this guy is indeed 0. So what is the object that is different from 0? So the object that is different from 0 is this object. You see, basically what I'm saying is that you can repeat the same argument I'm giving here for b minus 1 c1, for b0 c0, and for b1 c minus 1. Right? They're all annihilated by b, according to this rule. So every time you insert the anti-commutator of this pair, right, you can act on the destruction operator on the left and on the right, you will get 0. So the only way to avoid this derivation is that you insert explicitly some factors of C. So if you now insert here b minus 1 c1, right, one of the two terms, the one where b minus 1 is on the right, will not read this C1 because it will not read this vacuum because there is this factor of C1. So you can take summary, you can take this derivation, repeat it for the three pairs, b minus 1 C1, b0 C1, b1 C minus 1. You see that unless you insert these three objects, you will get a correlation function that in the operator language, in this Fox space construction, is 0. So we will define the conjugate of this vacuum, this 0 tilde, as 0 C minus 1 C0 C1. So this is just something that if you want to make the connection explicit between the operator language and this OPE description, if you want to calculate this OPE description by taking this mode expansion, you take this mode expansion, you plug it here, you take this mode expansion, you plug it here, right? And then you close this in the vacuum, right? You have to close this in the 0, 0 tilde. Now, this insertion of these three objects, as we will see in the next hour, is related to the 0 modes of the determinant that I was mentioning before. So we'll come back to this. But this provides the explicit link between this language and the standard operator language. Please. The statement here, no, what I'm saying is that this, if you take the scalar product of 0 and this guy, right, that's 0. Well, what I'm saying is that in this theory is not. In this theory, what is 1 is this. But what I'm saying, and you will see more, is that in order to have a non-zero correlator, you need to have the insertion of three factors of C. This 0 here is exactly related to one of these 0 mode in the path integral. The fact that you are integrating over a 0 mode. So what I'm saying is that any correlator that, right, if I put here, I don't know, if you take C minus 2, 0, right, and you sandwich that with B2, 0, or C2, whatever, that object is 0. right? It will only, for the same argument, right? You can repeat the same argument. You insert the commutation relation of pairs, right? And then you use this anti-commutation relation. You bring b minus 1 on one part, b minus 1 on the other part. You'll see that it's 0. So it is non-zero only if you have this insertion of these three objects. So that's very unusual. That's why I'm stressing that, right? That's strange. Now what we will do is to link this to the comment that I made in the path integral version where I said, oh, what if the determinant has 0 modes? Well, then I said we will need to take care about the 0 modes separately. Well, this is the operator language of taking care of that 0 mode. You need to insert in any correlator C minus 1, C0, C1. Yes. Yes.
You've shown with B's and C's that it's a null state. You can show easily with A's that it's not. So I don't see how this isn't a contradiction. Like I understand fully that you can say that you have to have an insertion if you have an excited state.
So, okay, we are, okay, maybe it's not, you are making a step too far in the sense, when we add a new sector of the theory, the BC ghost, right, then the 0 is not literally the same, right? Because now I have to tell you how the new sector, Bn, Cn, act on the new, on 0, right? So that's a larger, it's a vacuum in a larger Hilbert space, right? And I'm telling you that if you define that larger, the action of the new degrees of freedom on the vacuum of the full Hilbert space in this way, right? Then you will need, then you will, the non-zero correlator will have this form, right? But it's a very general thing, right? I mean, if I you will see, if I change the definition of the vacuum, right, you will always be, in order to get something non-zero, you will always need to make sure that you have this right number of C, and this is related to these 0 modes. So the fact that there are 3 is not by chance. More questions? Okay, then we can stop here.